That's all I got, Ben.
Okay, cool. And sorry, if I keep looking this way, I coach a little sixth grade basketball team, my son's team, and they're playing in the playoffs and they're in overtime right now. So I'm watching the score. My wife's texting me updates.
That's
Um,
so exciting. Keep us
yeah,
posted on the score too.
tied. Oh, yeah. All right. Overtime. Okay. Um, Quick note from me. I was starting to grade the study guide for this week. I didn't get all the way through. Yeah. Um, The one so far, everything looks pretty good. There was just one thing I wanted to address around the question about why do we use random and stratified random samples? And pretty much everybody that I saw got the gist. That you got it generally right. There was just one small little tweak I would adjust in some of the words some of you use, not all of you, but you talked about random samples guarantee representativeness, or it ensures that there's no bias in the sample. And I just wanted to temper that language a bit. Like random, that's essentially what random and stratify random samples are meant to attempt to do, but they can't guarantee that they're representative, or they can't guarantee that there's no bias in the sample. So I just wanted to throw that little caveat in there. I'm not taking points off or anything for it. I just wanted to make sure like we were all on the same page that random samples make sure that everyone in the population has an equal chance to be selected, and it helps to reduce the bias in the sample, and it helps to make sure that it is more likely going to be representative of the population than other sampling approaches, but it doesn't always guarantee that. And so even when we do things like random assignment into experimental conditions or randomly sample, oftentimes, and this is especially true when we have assigning people into conditions, we'll compare the two groups to make sure that there's no systematic difference on other factors. And so we do that, because we know that random assignment and random selection doesn't guarantee that. So anyway, you get the point. Just want to throw that caveat in there. But overall, it looks like you all did really well on those pieces. So that's great. Any questions on the study guide or any of the assignments coming into this week before we jump into the lecture? And
The
so I can check the
vignettes,
score too.
can you hear me right now?
Yes.
The vignettes, can we go over that a little bit? Just because I feel like I'm flying blind. I don't know if anyone else does on the vignettes. Hopefully, I've redone and gotten better, but I still don't know if I'm in the right direction.
Okay. Yeah, that's fair. I have not graded the, I'm trying to catch up on those. So I haven't graded all of the vignettes yet. We could probably walk through them, or what we could potentially do is I should be able to go through a good chunk of them before tomorrow, and we could spend some time tomorrow on them before the assignment. But in full transparency, I just haven't had time to start grading those. I don't know, Chris, I'm speaking for myself.
No, I've been a bit focused on the writing assignment and the data manipulation. So I've the vignettes of since the first one. And yeah, you've got the second and the third. So I have
Yep,
not.
yeah. So if it's okay, I will do that. I'll prioritize that before tomorrow's class, and we can carve out some time at the beginning of tomorrow's class to cover that.
I would also
Of
make sure
course.
make sure you guys are looking at the rubric too, and making sure you spend your time on the right things, right? The for example, the data manipulation exercise plus the paper are worth this, the same amount of points as all four vignettes combined. So just keep watching, and I know one's a 3-point class, one's in the 3 credit class, and one's in the 1 credit class. So I'm just kind of holding that equal for the sake of things. But like the stats practice that's coming up this week and the stats practice next week, like those are literally half the grade for the lab, right? So go back to the rubric and make sure you take a look at those, because that's going to help you also know where really spend your focus time on your out of class stuff.
Maureen, I think you have your hand up. Go ahead.
I tried to lower it. I thought that I only saw one scenario posted for the, I think it was like the final vignette one, but it said that we're supposed to have 2 scenarios.
Yeah,
I'm just trying
so
to find that real quick.
yes, you're right. Good call out. We're just walking through it one at a time. So this week we're going to do the one final scenario that's based on descriptive statistics, and we're going to be looking at turnover data. And next week it'll be inferential statistics where we look at customer service performance data. We were going to give you
So it's
both at
just,
once, but the tutorial that I released, I hope you guys saw the email that I sent yesterday afternoon about this. We're just going to go one at a time rather than dropping both on you guys at once. I think it'll be better to focus.
okay, so this week we only have to do one scenario for the vignette.
Yep.
Yes, and
Yep.
ultimately, vignettes 4 will be both of those scenarios, but you're only going to do one this week and one next week.
Yeah, go ahead, Becca.
I just want to get some clarification on the grading because I think in our all the classes we've had so far, we've had the opportunity, and correct me if I'm wrong, everyone else, because I don't know if I'm remembering this correctly, but we had the opportunity to resubmit for full points after assignments were due, or is that only if we got underneath a certain score? Does anyone remember what that was? I'm just wondering because, okay, it was a 3. So if you got a certain like low score, you could submit for a higher score. And I was just wondering if you both were approaching it differently or if that's a consistent like system throughout the program.
Can I jump in on that?
Yes.
So I felt like that was brought up because they wanted to see us actually complete the assignments because it feels like now I'm just working in the dark, whereas before the assignments were like I had to keep redoing this until I get it right because this professor is going to look at it and be like, no, you're not getting the concept. Is that how we should look at the data manipulation, the vignettes? Like, is that what you're getting at, Becca, where you're like, we're resubmitting it until we get it correct?
I'm not sure. I don't understand what you just said, Tyler. I have no idea what you just said. I'm
So
sorry.
basically, like I'm sorry if this is confusing. It's just all of the classes we've had before have had a similar type of approach to the homework assignments where if we aren't getting it and we get a low score on a homework assignment, we can resubmit it to get more points. And it feels a little bit different for this class where it's more your first shot is kind of the score you get, although we did get that second chance with the data manipulation. But I'm just trying to understand if that's just your specific approach to this class. And I guess this is maybe more of a Brit question. If
Yeah, there's no
I can chime
formal,
in.
there's no formal guidance. Oh, go ahead, Brittany.
okay.
Yeah, I can chime in. So I think part of the confusion with this is that the previous classes that you guys did, I was the course developer along with the professors until this course, where that shifted as I updated you guys on in the group me. So with that being said, the structure of Ben and Chris's class is different. So moving forward, instead of it being each of your classes will be pretty much united because I would be the common denominator. That's not really going to be the case anymore. So it'll be a lot more like what you potentially experienced in other academic experiences where like it's kind of each class is a case by case. So I'm sorry that wasn't more clear. I should have been a little bit more verbose in my explanation to you guys at the beginning. It did happen really quickly, so apologies for that. But yeah, that's kind of to clarify. So for Chris and Ben, what they say goes. Like what they say regarding the kind of assignments and whether or not you can do them again or not, or how they do the point breakdown, that's going to be their decision as the professors and developers. And that'll be true for your other courses moving forward, just so you know.
Got it. Yeah, I just wanted to bring it up because I'll speak for myself, but it feels like we're all kind of the same sentiment where we weren't sure that was a switch up. So there were certain things we thought would be consistent. And so we approached the first assignment thinking, or all of these assignments thus far thinking, oh, it'll just be consistent with before. So I just want to provide that context for everyone so we're on the same page. But thanks for that update, Britt.
Yeah, I think it's good feedback, and I'm glad we're clarifying it. We did get the second shot at the data manipulation exercise. The stats practice exercise that will be due this Saturday, the 47-minute video I sent you is literally the assignment. If you just watch the assignment, I'm literally doing the assignment on video, right? So you're not going to get a second shot of that, but I really hope y'all don't need it, right? Like you should be able to follow along based on the lecture content we do today. We're going to walk through the video that you also have to watch tomorrow. Like you're going to have plenty of ability to hopefully go back and sort of match. But to be totally candid, we just don't have time to go back and redo the assignments because we're trying to get through too much material in 8 weeks. So I think Ben and I have talked informally about when you get to the end of the vignettes, being able to kind of replace your lowest grade if you want to go back and do kind of get one replace your lowest from that. But beyond that and the gimme we got on the data manipulation assignment, this is gonna be kind of like real life where you're coming in, you're doing an assignment, you'll get some light feedback, and sometimes you'll get another bite at the apple and sometimes not. But we have been, I think, hopefully we're clear now that when you're handing stuff in, you're getting a grade for it, and that's your grade.
Bailey?
I was just curious, and maybe can speak for everybody, but maybe specifically for the vignettes, if we could get just a little more feedback. I understand like this is real life and like this is a master's program, but like for us, this is still like our first time learning this certain material. And so especially for the vignettes, because they're super confusing sometimes. And I know you guys are super busy, but if we're able to get a little more feedback on the vignettes, because I'd like to like learn how to build, because I right now don't feel like I'm doing it right. So that way it just kind of helps the confusion. I don't know. I know you guys are doing your
Yeah,
best.
once we can prioritize getting them graded. I think that's fair feedback. I would go back to the video because we spent, I don't know, I don't remember whether it was one class or two where we went very deep into this concept and rewatch some of that. That might be helpful. We'll continue to give you guys specific feedback on the actual assignment, but I think rewatching the content, re-engaging with the materials, right? When that's really the best way to kind of help yourself here, right? And we'll give specific feedback, but there's all the lectures from week 1. Can you post last week's lecture? Yes, you got that, Britt? Okay. But those will also be helpful materials in addition to the specific feedback that we get you guys.
We'll have a feedback for you tomorrow before class. Any other thoughts?
And thank you guys for being vocal about this. This is how the program gets better.
Okay. I think that was it for the preamble. Anything else, Chris, Brittany, from your side?
No, I'm gonna work on getting those videos from last week up and posted. I'm gonna start them tonight and hopefully they'll clear tonight, and if not, by tomorrow for sure.
All right, cool. All right, let us jump into we have a lot to cover today. This is really the heart of this course and getting into descriptive and inferential statistics. What we cover this week is essential for what you're going to learn next week. So this week and next week are going to be the 2 hardest weeks. And we just want to set the expectation. This is probably going to be the most data intensive weeks for sure. And so as Chris mentioned, we're going to try to really walk you through the activities and use the lab time to work together. So there's a few things that come with that in the form of expectation setting. One, really focus this week and next week in the lectures. There's going to be a lot of new content probably for many of you. It's not the easiest to grasp if it's the first time you're introduced with statistics or even the second or third. So really, really try to focus. We're going to try to, really engage in the exercises that we break out and do today and tomorrow. Chris also was kind enough to put together a scripted step-by-step video. It's about a 45-minute video. It is absolute must watch before tomorrow. Like tomorrow, the expectation is y'all are coming, have Excel ready on your machine. You've watched that video. If there's any trouble you have, troubleshoot that tonight or tomorrow morning so we can troubleshoot that before lab. But tomorrow we're going to get our hands dirty in Excel, and the descriptives is going to be based on what we do today. So in light of the discussion we just had, just wanted to make sure that we set those expectations, and we'll restate those at the end of class and also give you a chance to ask questions or have any concerns. But it's super important that you watch Chris's video before you come into lab tomorrow. All right. So today
They're
we're
all
going to talk.
posted. So
Go
the
ahead.
video is posted.
Go ahead. Go ahead.
Sorry, I was just gonna say the video is posted in the little. Can you guys hear me? Okay, the video is posted in the little study guide for this week, so you can find that. And the Excel document and the Word document that you'll need for class tomorrow is in the assignment that's due on Saturday, labeled I think it's called stats, the stats practice. So those are the things you're gonna need to tomorrow. They're already up. You can get to them now.
Okay, perfect. So this is the kind of flow we'll go through. We'll start with a very, very brief introduction to descriptive statistics. A lot of this hopefully will be somewhat familiar to you. We'll then introduce the topic of distributions. We've been using that term, but we're going to really explain what it is. We're going to try to visualize some distributions of data, different types that you're going to run into in organizational research. And then we're going to break it down into specific categories of descriptive statistics, namely measures of central tendency and measures of dispersion or variance. And we'll talk about how you calculate these different measures. Memorizing the calculations and all this stuff is not super critical, especially for the more complex ones, but understanding what they are, that is what we're trying to get across. So we'll hopefully we'll be able to pause periodically, let you dive in with questions throughout. Okay. So basically, descriptive statistics do exactly what the name says. They are describing or summarizing important characteristics of a particular data set. So imagine we had a big data set of performance data or turnover data or employee satisfaction data, whatever that might be. Descriptive statistics give us data or data points to help us make sense of that distribution of data or help us describe it to somebody else. And usually we're doing things like we're describing what the shape of that distribution looks like. Is it normally distributed, for example? Do they have a lot of outliers in the data set? We'll talk about what all that means later. Well, what's the center of the distribution? Where do the numbers kind of come together for the most part? Or how spread out is the distribution? Is it really wide or is it really tight? So these descriptive statistics help us to describe the shape of a distribution of data. But it is important to know descriptive statistics are, they are very valuable. They are essential for what we're going to do next week when we talk about inferential statistics. But alone, they don't tell us enough to make predictions or inferences about the population or the future. They simply are intended to describe what that distribution of data looks like. And as we're going to break down later, there's two big buckets of measures that we use to describe a distribution, and those are the central tendency, where does the data kind of align, where the values chunk up in the distribution, and how spread out are they. We talked a little bit about what statistics can't do. This is a great slide just to kind of have as a reference guide. But again, when we talk about descriptive statistics or inferential statistics, that word statistics implies that we're using sample data. And that's something we kind of fudge that sometimes in our normal language. We'll talk about statistics, even if we're using it for population. But when we're using that term statistics, technically, it means we're dealing with sample data. And sometimes it might represent the population, but just like in the study guide that you responded to, if we are taking a sample, and let's say, for example, we use a really poor sampling approach. So we use a convenient sample. We just happen to pick people who all tend to have certain characteristics, and then we create or describe the central tendency and the dispersion of that sample. That might not actually reflect the population. And it also doesn't really tell us or give us enough information to explain why. Why did we find what we saw? What's causing that distribution to look that way? Doesn't really give us that type of information. It also doesn't really give us enough information to say what's going to happen in the future. That's where inferential statistics come in. So again, this is a restating of the point that descriptive statistics help us describe a distribution of data, and that's pretty much it. But they are really, really important and really valuable in organizational research. So just having an understanding of what we're going to talk about today and tomorrow will make you really dangerous in a good way as an organizational researcher. So that's kind of the intro. Chris, anything to add before we dive into the meat?
Yes, if I could find the mute button. Descriptives are where it's at, guys. If I'm being totally honest, right? If you're not aspiring to be a research scientist or a PhD or in that direction, 80% plus of the statistics you're going to do in an applied HR career are descriptive. At least that's almost all I do in my applied life. I rely on smarter guys like Ben when I need an inferential test run. So this is really core and common to your day-to-day life if you're going to be using and doing evidence-based decision making. So I love descriptives.
Descriptives are really valuable. And I think you'll find, hopefully, as we get through toward the end of the session and we start to show you how to calculate them, it'll demystify it a little bit, because I know it kind of sounds, it's sometimes these things sound overwhelming, but really when you dig into them, they make a lot of sense. They make a lot of intuitive sense with the foundation of knowledge that you already have about collecting data and sampling and things like that. So I hope you come to that conclusion as we get through. So we'll start with a brief overview of these. We're not going to define them exactly yet, but I want to introduce them so you get the gist of it, so that they'll make sense when we start talking about distributions. And then we'll come back and we'll really define each of these from a mathematical standpoint. But basically, when we're looking at measures of central tendency, what we want to know basically is let's say we have a sample of data taken from an organization. Doesn't matter what we're measuring, but let's say we have a sample of data and you are doing some reporting in your organization. And one of the most common questions that you might get asked is, well, what's the average score in that distribution? Or what's the center of the distribution is often what is meant when that question is asked. What's the typical response, or what's the typical value in that distribution? What's normal, in other words? Those are different ways to ask the same question. And what we have are essentially three different ways, or three different descriptive statistics that we could use to describe the center of the distribution. There's the one that's probably the most common to all of us, or the most easily recognizable, which is the mean. And that's simply the average value of a data set. The second, which may be familiar to some of you, is the median. And the median, just like in a road, when you're driving on a boulevard and you get the median is the center. It's the center value of the distribution. So the median takes a little bit more steps, where you have to order the data set from lowest to highest, and then you count until you find the exact center of the distribution, and that becomes your median. And we'll talk about how mathematically they're different than the mean and when they differ and when they're the same. And then the mode is probably the easiest of these. It may not be the most common, or maybe not. The average is probably the one we're all mostly familiar with, but the mode's actually the easiest. And it's when we look at a data set and we say, which value is the most common? What was the most common or frequent value in that data set? And so as you can see, all of these measures are trying to get to what's a typical or what's the normal response in the data set, but all from a slightly different perspective. Averaging it, finding the center, and then finding the most frequent. And so we'll get to the specific calculations a little bit later. So that's central tendency. Now, there is also another category of descriptive statistics. Those central tendency tell us about the center of the distribution. Dispersion are measures of variance, you can use either term, measure how spread out the distribution of data are. How much do the data points in that distribution of data differ from one another? Do they tend to be very much the same? Or do they really differ a lot and that distribution is really spread out? This is another extremely important and valuable type of data point that you would want to know about a distribution of data. Now, there's a simple measure here, and then there's two fairly complex measures, as we'll see a little bit later. The easy one is the range, and the range is quite possibly the most simple to calculate. You basically take whatever the lowest value or the highest value. I'll start with the highest. We take the highest value in the data set and you find the lowest value in the data set and you subtract the two. And that's it. That number, the highest value minus the lowest value, that's your range. That tells you the full range, how wide or spread out that distribution is. But the range doesn't really tell you what's the typical difference between values in the data set. So if you had thousands and thousands and thousands of data points in your data set, that becomes a really important question. What's the typical difference between data points or values in the data set? And that's where the variance and the standard deviations come into play. So the variance and standard deviation, we combine them in the same one. We don't separate them out because they are inextricably linked. They basically are measuring the same thing in a slightly different way. We'll explain that a little bit more later. But basically, the variance and the standard deviation measured the typical dispersion, the typical difference that you would expect to see among values in your data set. And they're calculated very, very similarly. We'll get into the calculation, but for now, the standard deviation is simply the square root of the variance. And so we'll explain why that's important a little bit later. And I think you'll immediately understand why that's valuable and why that's important. So the first question I just wanted to pose, we'll take a pause because threw a lot out at you. Wasn't meant to go deep, but it was very surface level introduction. But now that you've seen these, I'm curious, where do any of these kind of like, oh yeah, I've seen that before. I've seen that at work. I remember when I took a class and we talked about that, or any ahas or any connections that you can make to how you've seen these used, how you've seen them effectively, how have you seen them misused? So you can kind of go wherever you want with this, but I'm curious to see how this resonates with you, where you've seen these before. Okay, Becky, you had a good one. I can take that really quickly. Example, actually, you know what? Hold that one because I think it'll be much easier once we actually show you a little distribution of data and we'll calculate it. And it's much easier to understand the variance once you understand the average and other statistics to get to that point, because you actually have to calculate central tendency before you calculate variance. So I'll get to that. But where have y'all seen some of these before? Let's start there. It looked like some of y'all took statistics before. Some of
I
y'all
haven't
didn't.
seen any of this, but I use this is it's kind of been interesting because I use a software called MicroStrategies for my job. And it's a lot of data for like sales data for like regions and sales managers and district managers on the volume of Tito's sold. You can look at it as the dollar amount or the supplier cases, and you can kind of manipulate that data to read it in a certain way. And so I'm curious on what that data would look like using central tendency, or like would I use dispersion or range to look at sales data within regions or territories?
So Ben, could I double
Go
click
for
on that
it.
one a
Yeah,
little
go
bit?
for it, Chris.
Yeah, sales data. I'm glad you guys brought it up, and Stuart, you dropped it in the chat. Sales data is a great way, a great place where you see descriptive statistics used really well. And the reason for that is for one very simple driving fact: commission and pay, right? Because what we need to know if we're going to drive and motivate salespeople is how much is reasonable to sell, and then ask them to sell a little bit more than that, right? And then use your commission structures and your incentive packages and the way that you drive behavior for sales folks by using what you know about sales data and then creating quotas and goals and incentive spots based on what we know. Now, the amount of Tito's you're going to sell in Topeka, Kansas is different than the amount of Tito's you're going to sell in New York City. And so you can't give them both the same sales goal. You have to understand how the data varies in different stores for different products, in different places for different times of year, right? The sales quota a week before Christmas is not the same sales quota as September, right? Because of what's normally happening within the business at the time. But that is all based in the descriptive statistics and specifically the distribution. So if you look at raw sales numbers for any given week or time period, you're going to see a distribution that is probably somewhat normal, but it will be a little bit skewed. When you take quota adherence, it will almost always be a perfectly normalized distribution. And that's because most people are going to hit their quota. A few are going to be above, a few are going to be below, and you're going to get that nice bell curve that Dr. Ben's about to get to. But sales is a really great example.
These are all really good examples. Stuart, Chelsea, Tyler, great. Those are perfect examples of how you would see this kind of stuff come up in everyday life or a typical job, and why and exactly what Chris was saying, why understanding this sort of data is important, because understanding what a typical distribution of sales data or performance data, whatever kind of performance metric we're using, that makes a material difference in the decisions we make about managing human performance. They make a material difference in terms of how we hold people accountable to goals and targets in an organization. And so that is, you can see just through those simple examples that we all threw out there, why understanding this is so critical to what an organizational psychologist does. Even if this is the last research methods course you ever take, which hopefully it's not, but let's say it is, right? And you're after this, you're like, I never want to see stats again. That's cool. That's cool. Hopefully we don't scare you off too much. But if that's true, you will run into this stuff again. You absolutely will run into this stuff, even if not for, hey, understanding if you go into learning and development, and we're going to have some examples a little bit later, and you're giving post-training evaluations, and you're trying to test whether people understand the knowledge you just deliver to them via the training course, or you're in leadership development and you're measuring transfer of training, or you go into performance management. Understanding of central tendency and dispersion, must-haves to understand this, because the decisions you make as a practitioner are going to be dependent on your understanding of the typical distribution and the typical spread of the data in those various distributions of data. So this all sounds very abstract. It is. That's one of my reasons why I asked the very first question in the study guide, why statistics is one of the most nascent fields. But I will assure you, both me and Chris, This understanding of this stuff is crucial to just about anything you decide to go do with your IO degree. So hopefully in the next little bit, we will demystify some of this and we'll make it seem not as scary. So that's our goal here. So let's talk about distributions. We've used that term a lot already in the course. We use that term already today. What the heck does that mean? Well, basically a distribution is just a collection of data points. And so we'll go through this slide kind of quickly. I'm going to break down different pieces, but I'm going to go bullet by bullet here because this is really important content. A distribution really is just all of the values that you are measuring or collecting in your whatever becomes your data set. That could be, in this case, we're using the average units sold by a sales rep per month. It could be what we're going to introduce some call center data to you in one of the project data sets. That's going to show things like how long does it take for a call center rep to complete a call with a customer? It's going to measure things like how many calls per day can a call center rep go through in a typical day in a given month, for example. So whatever you're looking at, the distribution is just all the data points that you've collected. Could be all the survey responses from a sample of employees responding to a survey. Whatever that might be, the distribution's just all those data points. And what we also know, and what's kind of visualized here, is that usually we're dealing with samples of data. Sometimes we have populations of data, and that is fairly common. We talked a good bit about that. And what you'll notice in this visual, and this kind of connects to these two points here, what you notice in this visual is that imagine that this red line is the universe of all the data in that population. Let's say, for example, it's all of the employees in the sales organization, every single one of them, and it has their sales performance data. Average units sold per month. So that's what this red line represents. Now let's assume that we can't access all that, right? Let's say you're in one region, you can't access all that data, you don't have access to it. So we know that there's this distribution that exists, but we don't know exactly what it is. We don't have access to it. And so what we have access to, though, is a couple of different samples. And so that's what you see here. You see all these little XA, XB, XC, XD. What that represents is the average of 4 different samples that you take from that population. And this is just a purely hypothetical, but this remember, again, this big red represents the full distribution, all sales reps. XA might be the first sample you take. Let's say we took a random sample of all these reps, and then we calculated some numbers, some descriptive statistics, and then we took another sample. That's XB, that second little curve. And then we took another, and that's this big tall one here. And then we took another, XD, and we took 4 different samples. And what you'll see, and it's pretty typical, is all these samples don't exactly get to what the population looks like, but they're all pretty close. And the more samples you take, and then let's say you start to average the samples, then you get pretty darn close to what the population distribution looks like. So this visual is a really good one to describe what an organizational researcher is typically doing when we're doing samples. We're taking samples that are imperfect measures of the population, but they get us close to what the population looks like. So let me pause for a second. Yeah, go ahead, Chris.
I have one thing to add. Anytime you have an ordinal or continuous variable, meaning the order matters, you can create a frequency distribution, and you can see how often something occurs, right? I put this in the chat. And the reason I'm saying it that way is in an HR profession, you're often going to want to know what was the tenure of people when they quit? How much do we pay people? How well did people do on the test, right? All of these things, and the bell curve, the distribution, the frequency distribution is the body of your data. It's the rawest, most telling way for you to go look at your data. And it's going to tell you about your measures of central tendency and your measures of variance. But you can and should, in my opinion, learn how to look at a bell curve the same way that the guy in the matrix could like see the matrix with the, just by looking at the code. Like that's the level that you should get comfortable with distributions, because any continuous variable you have in your HR data, you can put into a frequency distribution. And it's so critical to understand what a distribution is telling you. I'll try not to get on too many soapboxes, guys. I'm very passionate about descriptive stats.
I might have a silly question.
No silly
So
questions. Go ahead.
So the big red, that's our bell curve, and that is the population. But wouldn't we have to do the samples first in order to get that population bell curve? Like how do we
Oh,
obtain that information in the population first?
good point. Good question. That there's no silly questions here, by the way. That's a great question. The red, for this example, where the red is a unknown distribution, we know that there's a distribution of data, but it's theoretical and unknown at this point. And so, but for the sake of illustrating what happens in sampling, we're pretending like we do know what it is. So the red, sorry, it's so that probably wasn't the best answer, but you are correct. Maybe I'll answer it this way, Chelsea. In a normal case, if we're doing sampling, that probably means we don't have access to the population data. So you're not going to have that red distribution. You don't know what it is. You know that one exists, but you don't know what shape it is. You don't know exactly what the mean is. You don't know what the average is. You don't know what how the tails look. You don't know what that shape is.
Think about
in
voting.
this
Voting
hypothetical,
populations are a great example here. We can't know how everyone's going to vote. There's no such thing as that population. But the red curve that Ben put here is that imaginary reality.
right?
And we're doing a lot of different samples so we can generate evidence so that we can approximate and predict that reality. So we don't know how everybody's going to vote on November 4th. But if we go out and we sample a bunch of people and we create these samples, we can approximate what the reality is and potentially describe what we can definitely describe what we've seen, but then we may be able to predict what's going to happen.
So we can take our samples eventually and create whatever shape that bell curve would be, whether it's skewed or not skewed based on the samples we collect.
The sample, yeah, sorry, maybe this was a bad example I gave. That's not exactly the way it would work. We would only be taking a guess at what the population distribution looks like if we were gathering sample data. So if
Okay.
we were starting like in a real life scenario, imagine the red distribution is not there. We don't know what it is. And we took 4 samples from it and we got those 4 black ones at the top. Those would be our 4 best guesses as to what the shape of the distribution looks like. And we won't get into this. This is a little bit too complex for this course, but there is a measure that some of you may have heard before, the standard error, the mean. And what that means is like if you took a bunch of samples from a population that you didn't know of, you took a sample and 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 a sample, like in polling, then you take the average of those, and that's your best guess as to what the population distribution looks like. It's still unknown, but you could take a pretty good stab at it.
Is it pretty normal then that you always kind of see these guesses of these bell curves? They always look the same. They always kind of like I guess maybe in all the examples I've ever seen, it's the same shape, just about.
We'll talk about different shape distributions and when you might expect to see a bell curve, and also when you would not expect to see a bell curve. So we'll get to that. That's a good point, Chelsea. The bell curve, or the standard normal distribution as it's technically called, is the famous one because it's got some really important characteristics that we use and some assumptions that we make when we use to conduct inferential statistics when we get into next week. I'm trying not to complicate it here, but it doesn't, the short answer is there's no guarantee that there's really no guarantee you're ever going to find a true normal distribution. But generally
shape of the-
speaking, that's the one we typically use to compare to.
The shape of the curve dictates what you can and can't do with it statistically,
Yep.
and what statistics are appropriate to use to describe it. So when you watch the video tomorrow, you'll see a significant example of that. But the short answer is no. The slightly longer answer is you have to understand what the curve looks like, because it's going to rule out certain stats you're going to want to use either inferentially or descriptively to intelligently describe the data.
These are great questions, by the way. I just want to keep encouraging you. This is exactly the type of questions we need to be asking. Keep them coming, please. One of the things that Brittany put in the chat that's I think is a really important point that I didn't mention, and I'll explain it here, is, and ignore the text on the slide. Let's just take this bell curve again, this bell curve that you saw. There's basically two axes, right? You have your x-axis and then you have your y-axis. And in the distribution here, what we have on the x-axis is all the different possible values in your distribution. So you're basically just plotting them low to high. The lowest value, on and on and on and on till you get to the very highest value. So the x-axis represents the values. The y-axis represents how often you find each value in the distribution. And I'm going to show an example of a really, really stinking simple distribution a little bit later. That'll be helpful to visualize this. But essentially, that's all we're doing is we're taking what values are we finding in this distribution and how often are we finding them? It's called a frequency distribution. How frequently do you find each value? And typically, in a distribution, to a bunch of the points in the questions I brought up, in a normal distribution, what you would find is that more values, there's a higher frequency of middle values than extremely high values, and also more middle values than there are extremely low values. That's typically what we would find. And what's interesting is that if you look in the general population, when we're talking about humans, you see a lot of characteristics that are generally normally distributed. Weight, height, IQ. If you took every person on Earth, or let's say just every American, for example, and you stacked them up from height, lowest to highest, and you put them in the distribution, and you put, how many people are 5'10"? How many people are 5'9"? How many people are 5'8"? And so on and so on and so on until you get to the highest and lowest. The distribution would look very much like that. It would look like a normal distribution, a little bell curve. If you did the same thing with IQ and you took a standardized measure of intelligence and you gave it to the full-blown population, you put the lowest scores and you stack rank them to the highest scores, you would see the same thing. See a normal distribution. This does not guarantee, however, that all distributions of data are normal. And you can see that here at the bottom in bold. This is especially true when we're looking at human performance. The distribution of human performance is not always normal. In fact, in organizations, when you look at the impact of human performance on the organization, it's definitely not normal, meaning that you have a very, very small number of people that have a huge, dramatic, outsized impact on the company performance. We won't get into that. But the point I want to make really clear is that the normal distribution, we're going to use it a lot. We're going to talk about it a lot. It has some very important characteristics, but not all distributions are normal. And as Chris pointed out, we're going to work with some distributions tomorrow that are not normal, in fact. And we're going to talk about how that changes the way you look at the data and you work with the data.
I'd like to bring Becca's question back up here because you have this normal distribution with the percentages here, and it's a great opportunity to talk about variance and standard deviation. So I'm sorry if I'm skipping ahead, Ben.
A little bit, but that's cool. Go ahead. It'll be good to touch on it a couple times.
These percentages kind of show what percentage of the overall population in this case are at what point as a distance from zero. And zero here is the average, right? It's the mean. The way you calculate variance, I'm not going to go into the formula, but you can think about it as a distance from that mean. And a standard deviation from that mean, the normal amount of distance from the mean. That's basically what the standard deviation is. So think if you had 100 friends and they all live in different places that are some amount of distance from your house. If you calculated how much time it took for each of your friends to drive to your house, and you added them all up and you took the average, and then you subtracted that average from each of the different friends' distances, you're going to get a normal distance, a standard deviation of how far you are from the average. If that number is really, really high, it means some friends live really, really close, some friends live really, really far. So you would get a very big number there. If everybody lives the same amount of distance from you, you're going to get a very small number there. And so the shape of this curve, whether it's really fat or really skinny or really tall or really flat, is a function of where the data points fall relative to that measure in the center. And it's an incredibly important concept when you take your average and you compare it to your standard deviation. It's an extremely powerful way to, at a quick glance, understand what's going on in your data. I hope that helps answer your question a little, Becca. And sorry if I stole stuff from later, Ben.
No, I think that's great too, because that'll help kind of bring hearing and seeing different examples of these points brought up at different times during this, I think will help this point stick. You can ignore the details in this for now, but we're going to come to what all these numbers mean in a little bit, and these become this visual right here is a super important visual, and one that you're going to be using throughout the exercises that we're going to do in class today, and also the stuff we're going to be looking at tomorrow. But we're going to explain what all that stuff means in a minute. Let me pause for a second and just see if any questions so far about distributions, anything we've talked about so far. There was no stupid question here today. Or tattooing it. Yeah, not a bad, yeah. That would be a pretty tight tattoo. I don't know. I don't know if my wife would
You are
approve
such
of
a nerd.
it. Yeah. Sorry, I was about to make an inappropriate joke. Not for the class. Okay. All right. So let's talk about characteristics of normal distributions. These are also these points actually explain what you saw in the data on that prior slide. And we're going to further break it down. So if it doesn't click here, that's okay too. We're going to get to that point. But a normal distribution, there's a couple of really important characteristics to it. One, it has perfect symmetry. So if you cut it right down the middle, and let's go back to that visual, if you cut that normal distribution on the right down the center, straight down the center, you notice a couple things. 50% of the data is on the right side of that cut. 50% of the data is on the left side. It's perfectly symmetrical. The tails, what we call that at the very end, where the frequency of the values get very close to the line, the x-axis, that's called the tails of the distribution. We're going to talk a lot about that when we talk about skewed distributions, what the tails look like. But if you notice, they look exactly the same. They're perfectly symmetrical. So that's a really important characteristic of a normal distribution. There's also another measure called kurtosis. I'm not going to talk a lot about that. Chris may have some thoughts on that. I don't typically use kurtosis very often. Chris, if any thoughts on the kurtosis of the, we'll talk about skew, but
Yeah, kurtosis is not super well understood, even in folks that do stats. But essentially, kurtosis is a way to understand how many outliers you have. In a leptokurtic, you have very, very significant outliers. So it makes your curve look kind of pinched because you have lots of really significant outliers. So it's tall and skinny. Platykurtic, which is the other fancy word, is no outliers. So you don't have that nice bell. It just kind of goes dunk, and you got no outliers. Now, to Ben's point, for like inferentials and stuff like that, it's not super important as a measure, But when you're thinking about outlier management, which is a big part of what you'll do when you're cleaning data and working with data, that's kind of what kurtosis is. It's trying to understand, do you have not enough outliers for it to be normal or too many outliers for it to be normal? And that's all we'll say about kurtosis.
And to answer Becca, Tyler, your point, let's parking lot that one till we get to I'm going to introduce you to a really, really simple distribution of data that we're going to work with. And it'll become a little bit more clear how the variance and the standard deviation are related to each other and are different. So just hold that thought for a second. So essentially, a normal distribution is perfectly symmetrical. The right side of the distribution looks exactly like the left side of the distribution. It also has this very interesting characteristic called the 68, 95, 99.7 rule. You don't have to memorize that. But what you will find as we start to look at it, what a standard deviation is, once we calculate it, once we show you how that's calculated, what you'll notice is that 68% of the data in the distribution fall within one standard deviation. Let me show you what that looks like. So essentially, if you notice, the center of that distribution where we have the mean, median, and mode cuts right through the middle of the data set. And then you notice in this dark shade on the right side, and then there's a dark shade on the left side. If you combine the dark shades of data, all the data that falls within those, you'll notice if you look, there's a 1 down here and there's a -1. That represents one standard deviation higher than the mean, and then one standard deviation lower than the mean. 68% of the data in your data set fall exactly between 1 and -1 standard deviations. In a normal distribution, you know that right off the bat. 68% of the data fall within one standard deviation from the mean. When you go out to 2, what you'll notice is it kind of comes down, so that line gets closer to the x-axis, right? And you see that little lighter shade of blue. And there, it's a much smaller percentage on each side. It's 13.6 here, between 1 and 2 standard deviations, and then the same exact amount, 13.6. So you add all that up, and what you end up getting is this magical number of 95% of your data fall within 2 standard deviations of the mean. Now, 95, where have you seen 95% before in this class? Can anybody remember? You did an exercise coming into class with 95.
The sample size calculator?
Yes. And what
Confident level.
confidence level, right? That number is not that 95% confidence, that's not an arbitrary number. That is associated with the fact that 95% of the data fall within 2 standard deviations of the mean in a normal distribution. 95%, if you took 1 and subtracted, let's say 100, right? Or 1, you subtracted 0.95 from it, what would you have left? You'd have 5%, right? So 5% of your data fall outside of 2 standard deviations. There's another value we're going to talk about next week called the alpha the alpha level. And oftentimes, have y'all heard, maybe by a show of hands, have you heard of a term like P less than 0.05? Does that sound familiar? P is less than 0.05. Have you heard of that before? If you've heard of that, that's not an if you haven't, that's okay. We're going to get to that next week. If you have, it's not an arbitrary number. P less than 0.05 is exactly associated with the leftovers in the distribution. Of 95% of your data fall within 2 distributions, 5% are on the outside. So those numbers are all related to each other. When we talk about confidence level and calculating a sample size, 95%, that is associated with the fact that, again, 95% of your data fall within 2 standard deviations of the mean in a standard normal distribution. And there's a reason I keep restating that. I'm restating it because it's so incredibly important for us to understand. You're going to see that come up over and over and over and over in statistics. P less than 0.05, the alpha level being 0.05, 95% confidence. That's where all of this comes from. It comes from what we know about a normal distribution and how much data falls within certain standard deviations of a distribution. Let me pause there for a second. Let's see. Whoa, before I do that, one other really important characteristic of a normal distribution, the mean, the median, and the mode are all exactly equal to each other in a normal distribution. And you'll see that played out here. Now, this is a perfectly normal distribution. And most of the distributions that we're working with in organizational research, that's not the case. You're going to see some data tomorrow where the mean, median, mode are not the same. You're going to see some data later today of a simple distribution where the mean, median, mode are not the same. But in a perfectly normal distribution, those three measures of central tendency are exactly the same. The mean, the median, the mode are the same number in a normal distribution.
And a quick
Okay.
life hack on descriptive stats is that you can calculate those three numbers typically pretty easily in any data set you have access to. And if those three numbers are not the same, it gives you a hint about where you need to start digging around the shape of your distribution.
Okay. So that's normal distributions. That's the bell curve. If you've heard of the bell curve, a bell curve, a normal distribution, and then the most technical way to call it, the standard normal distribution. All those things pretty much represent the same thing. Okay, now let's talk about some different.
The histogram, right, Ben?
Say that
I just
again.
wanted to put that last vocabulary out there of a histogram, which is, I think, isn't that a
Yeah, that's true, and that's true. And when we get to data visualization, we're going to talk a lot about histograms and why they're important. And when you create a histogram, you can usually in the stats package, even Excel, you can have it create a line that shows what that little bell curve or that curve distribution, what the curve of the distribution looks like on top of the histogram. Yeah, that's a good point, Chris. Okay, so let's talk about probably the more common scenario in organizational research where the data is not exactly perfectly normally distributed, especially when we're working with sample data. It's not, even if the population data is normally distributed, and actually, let's go back to that for a second. Let's say in this example, right? Let's say we were measuring something where the population distribution was perfectly normally distributed. Even if that was true in the population, when we create samples from it, that's probably not going to be the case. There's always going to be some slight difference in the sample data, and it's typically not going to be perfectly normal. But generally, when it's close to normal, we know these characteristics come into play, and this becomes really helpful. This really helps us understand probability and what a distribution is showing us about the probability of finding a value of a certain amount in the distribution. And that's exactly what we do. That's what we're going to be doing next week. Okay. Sorry, we're getting ahead of ourselves. You can tell we get excited about this. Non-normal distributions. Let's talk about a couple very common ones. The most common that you will, or I shouldn't say that. Some of the most common that you'll run into beyond just normal distributions are what's called negatively skewed and positively skewed distributions. And so you see two really basic examples of each of those. I'll start with the first one, negatively skewed. That correlates with or corresponds to this visual right here. A negatively skewed distribution is where you might find a lot of data bunching up on the high end of the distribution. And then there's this long tail off to the left side, off to the negative side, so to speak. So that's where the distribution gets its name, from where the tail points. So you notice here the tail of that distribution where that line gets really close to the x-axis and it gets real thin, that's pointing in the negative direction. The low numbers, the negative direction. That's where we get the name negative skew. So just remember the name of the name of it is where the tail points. A positively skewed distribution is the opposite, exactly the opposite, where you might find a lot of data on the low end of the distribution, and then the tail gets really long toward the positive end. So let's talk about some real life examples of that. And I gave you some examples here. So let's talk about a negatively skewed distribution. This might be things like if you were to, let's say you were training professional and you put everybody through this training course, and then after the training course, you gave them a test. And usually you expect that test to be pretty simple in an organization. You go through the training. If you went through the training, you should do pretty good on the test. Well, if you then calculate the distribution, let's say you had a bunch of 1,000 people go through this training course in your company, and then you took all the test scores, what you're probably going to find is that most people do really well on the test. And there might be a handful of people, a few people that do really poorly, but they're not going to be that many. That might be what this distribution looks like, right? A lot of people score really well, and then there's a handful of people that maybe didn't take it seriously or just struggle with the content, but it's not going to be that many. Another good example, age at time of death would also look like a negatively skewed distribution. Most people die at higher ages. Very much fewer, relatively speaking, die at younger ages. Sorry, that's a very morbid example. GPA values is another example where you would tend to find negative skew. That's a good question, but a good question is why? Why wouldn't GPA be normally distributed? That's a real question. Anybody take a stab at that? Why would GPA be, why would you tend to find more high end GPAs than low end?
Well, GPAs don't really go negative, and I feel like the mean GPA, like they all kind of sit between 2 and 4-ish. So
Right, but why? Is it because nobody gets 0 to 2? What happens to people with GPAs of 0 to 2?
They drop out.
They drop out. They're not in the distribution anymore. Exactly.
And what's the
Stuart.
other reason? The other side, what's the other side of the tail? There's a cap. You can't get higher
Exactly.
floor. It's called the ceiling effect and the floor effect. Oftentimes a variable can't go above or below a certain range, but it can go on forever in the other direction. And that's one of the reasons you often will see skew. Tenure is another good example that's usually positively skewed. You can't have less than 0 tenure, but you can have an almost infinite amount of tenure. And so it affects, skew is basically a quantification of the asymmetry of outliers. I know that sounds like but what you're saying is the outliers are not symmetrical, and we have more on one side or the other, and so the tails are not equal.
Yeah, exactly. That's a great point, Chris, about the ceiling and the floor effect, is knowing where the max and the minimum values are. And oftentimes when there's a minimum value or a maximum value, you're going to see some natural skew in the distribution. And that's very common, very, very common in a lot of the data that we're going to be looking at as IO psychologists. So that's negative skew, right? Again, the idea is that the tail where the outliers are points in a negative direction, and we call that a negatively skewed distribution. Most of the values tend to hover on the upper end of the distribution, and then they might hit a ceiling where they can't go any higher. GPA is a great example. Positively skewed distributions. Let's look at some examples of that. Wealth and income. This is a great, great example where you tend to see more people having low-ish wealth and income. And then when you get to the extreme high values, right? When you start getting to 500K a year, 750K a year, $1 million a year, 2 million a year, there's some people that make a ton of money, and it goes on pretty much infinitely, right? You got Jeff Bezos way over here and Elon Musk off the charts on the right, and Mackenzie Bezos way over here, right? I don't know her maiden last name, forgive me, but they're way over here. Bill Gates, Melinda Gates, way over there. We don't even see them on the distribution because they're so high, but you can't go lower than zero, right? So wealth and income tends to follow a positive skew. Same thing with compensation data. If you're looking at compensation data in an organization, you're going to see something that looks very similar. If you had scores on a difficult test, right? So let's say before you went into the training course, you gave them an assessment because you wanted to do a pre and a post assessment. So you gave them a really difficult test. Let's say we gave you a statistics test right before this class. Y'all would have bombed it. I would have bombed it. Chris would have bombed it. Everybody would bomb it because it's complex and it's not easy. And most of the stuff we don't know. We just don't know it. And so we would have been, that distribution of data would have been extremely negatively skewed. There would have been a couple of us who, oh, I remember that from high school. Oh yeah, I some of us would have known some of it, but it would have been very positively distributed. Sorry. Our points scored by players in a basketball game. We lost, by the way. Bummer. Lost in overtime tonight. That's okay. But anyway, how many points they scored? That would also be. You got LeBron James way over here, Michael Jordan's way over here. But everybody else scored 2 points, 4 points, 8 points, 6 points. Not many people scored 45. So that gives you an idea of what sort of, there you go, Chris, what sort of distributions and positively and negatively skewed. So any questions about skewed distributions? Okay. This, I won't go through this. We went through, I think, a good bit. This is a good little cheat sheet for you. Another type of distribution we will sometimes run into in organizational research, good to be aware of, is called a bimodal distribution. And a bimodal means exactly what it sounds like. So we talked briefly about the mode. We're going to learn how to calculate the mode later. But the mode is, again, just the most frequent data point in the distribution. And a bimodal distribution means exactly that. You have 2 peaks. So you can see that here, 2 peaks in the distribution. That would be called a bimodal distribution. Some real life examples of that. Restaurant hours. If you ever look on, like, you're trying to figure out when to go to the restaurant and you look at the peak hours and you look at the time of day and you see 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it goes back down. It's bimodal distribution. Or if you looked at what's the typical speed limits in the US on roads, you would probably see a bimodal distribution. You're going to see a lot of speed limits around 25 to 35, not as many around 50. And then when you get to 60 to 75, a lot because of the interstates. And so that's another good example of a bimodal distribution.
Hey Ben, could I throw an example out there of one you'll see at work? If you work at a company that has a large frontline population, if you were to make a frequency distribution of average annual income, you'll have your frontline employees clustered around that $15 to $20 an hour, so that 40K a year-ish. And then you're going to see another peak probably in that 60 to 80 range where your software developers and your office workers and your white collar workers are. Now, if you were going to take your average employee comp, it's going to fall somewhere in the middle there, and it's going to feel kind of inauthentic because you're going to have this big peak at 40K, and then you're going to have this lower but significant peak at like 80K, and then you're going to have a long positive tail for your senior executives, right? So an average there probably isn't really telling the story of those 3 worlds. Your average frontline, your average corporate, and then your executives.
That's a great example. And when you find that, when you see things like a bimodal distribution or even a multimodal distribution, these are a little bit more rare. You'll find them. Chris actually just described a multimodal distribution. that might tell you you got 3 different populations in your data. Might tell you you're combining, right? You're combining 3 different meaningful groups that could be broken out into separate distributions all into one. And so that's sometimes what you might conclude if you see something like a frequency distribution or histogram that looks kind of like this. But it is good to know that these are these are the types of distributions that you might run into. So we talked about normal distributions. That's the key, the bell curve, the standard normal distribution. We're going to come back to that over and over and over again. We talked about negatively skewed distributions, positively skewed distributions, bimodal, and then again, just to be aware that there are sometimes multimodal distributions. And then just again, just some descriptions of that. We won't go into a lot of detail on multimodal distributions. Okay, so let's take a minute and we're going to do some breakouts and really kind of take a minute to let this simmer and start to get active with some of this. I'm going to take a screenshot of this, and Brittany, if you wouldn't mind helping me we're going to go into groups. Let's go into groups of 2, I guess, like we usually do. Or I don't know, we could switch it up too. We could go into bigger groups if you like. Could do.
I got the screen cap for you, Ben. I got it covered.
Oh, you got it? Oh, thank you. So what we'd
Yeah,
like to
totally up to
do,
you.
let's do
How
groups of
many
3. Let's just
groups
do
of
it
3?
different this time. Yeah, what the heck? So what we're going to try to do is take each of these 3 very simple scenarios, and I'd like you all to take a stab at what type of distribution would you expect in each of these 3 scenarios. Would it be normal? Would it be negative? Would it be positive? Could even go outside of it. Maybe you heard something today and you think, I think that might be a bimodal distribution. The key is explain why. So let's take a few minutes in our groups of 3, take about 10 and take each of these. What distribution do you expect to see? Why? And then let's come back to the group and we'll go through it.
Ben, how long would you like the rooms to be?
10 minutes, please.
10 minutes. Okay, and a couple of the rooms have 2 participants because of numbers. But okay. All right. Okay, rooms are opening. Oh, Tyler got kicked out. Okay, he's back. All right, rooms are opening. Have fun.
Okay, we'll see you in 10.
Okay, Tyler. Okay, moved. Oh, good. Okay, we figured that out. Okay.
All right, so we got a lot to go through. Let's go through real quick. Any brave groups? Let's do 2 groups. If one group wants to fire away real quick. Who wants to go quickly? Got a lot
I'll
to
go.
Okay, cool.
Well, I'll just go with the first one. You're plotting total annual compensation for all employees in organization, including all departments and levels. I believe it's a normal distribution because it's a general population, and then you have your subgroups, meaning entry level to C-suite positions, and you're literally going to get averages of each subgroup, which build the general population, as you guys explained during the lecture today. So that's why I went with normal distribution on this one.
Okay, does anybody disagree with that?
I absolutely disagree.
Tyler, what do
I
you
think it's positive.
Positively skewed.
Yes.
What is that? Why, Tyler?
We had a very hard discussion, basically because you're going to have more people making less money than people making top dollar. So that's going to be a smaller group over here with a WISP.
That probably is more likely. I think you're thinking there, though, Stuart, is the logic you're using of the different groups of people who had different distributions being part of it's right on. But I think Tyler's point's right, is that you're going to have far fewer people making high values than you do lower values. So you're going to have that distribution is going to kind of look like, I'm trying to do it for you all. It's going to be on the low end of the distribution. You have a lot of people. You might have a couple of bumps here. And then when you get to the high end, the executives, that's where that tail gets real thin and long. That's what I would expect too. I'd expect a positive distribution of compensation.
So, a fun thing to do if you're a nerd like me and Dr. Ben is if you made a pivot table and you created a frequency distribution of exactly this total annual comp for every employee in your company, and you made a histogram out of it and you graphed it. And then in the filters, you put job code. If you filter for any given job code, it's going to create a normal distribution. But then when you take all the filters away, it'll go back to a positive skew, right? And that's because good finance departments calculate a percent and range, and then the amount that people get paid in a range is almost always normally distributed because finance manages a certain spend
Right.
per level, per job code, per job family. So you can go back and forth between this positive skew and a normal distribution just by turning on and off the job code filters. Try it out. It's fun.
Hey, what about the second one? That's good. All right, so 360 assessments of people leaders. We know that people tend to rate people positively in those 360s. What sort of distribution do we expect?
Negative.
Negative, right, right. And explain that a little bit. Why?
Because if most people rate positively, then the majority of values are going to sit on the higher end, which leaves the tail skewing towards the negative side.
You got it. You got it. Excellent. Good job. Yeah, that's exactly what we would expect to see. In real life, that's actually what we tend to see with 360s for especially for performance, is people tend to be very nice. And to Chris's point, there usually is a high end. You can't get higher than a certain score. You can only get, like, let's say 1 through 5 on each competency you're getting evaluated on. So you can only get to a certain amount. So you're going to see that distribution kind of like negatively skewed. Very good. And then the last one, this one's a little different. This was a little tricky, right? You're looking at offer decline reasons, and you start looking. You have 10 possible reasons that people choose from, and you notice that people pick 2. What sort of distribution would that look like?
Bimodal.
Bimodal. Nice. Yep. It would be a bimodal distribution. And that distribution is different. We didn't talk a lot about this, but this distribution is not going to be of numbers that are continuous, right? And that was one of the questions we asked in the readings about discrete and continuous variables or categorical variables. But one of the things you'll notice is that in this third example, we have categorical examples. It's not values. It's 10 possible categories. And of those 10 possible categories, there's 2 that most people will reply to, and that would be a bimodal. Yeah, nicely done. Good job, guys. And even in the case where you didn't get it exactly right with the distribution, the logic was there. And so that's a great sign. Okay, so let's get into measures of central tendency. We'll try to get through this section.
And Ben, quick answer to Marina's question. You
Yeah.
can't really have positive and negative skew with a categorical variable.
Correct.
Because positive and negative skew implies directionality in the x-axis. So in this case, if the variable is categorical, one comp or one turnover reason is not better or worse or higher or lower than another. It's categorical.
Yeah, great point. Great point. Okay, measures of central tendency. Again, we're going to come back, as one of the reasons we talked about distributions is because understanding distributions of data is critical to visualizing and understanding what these measures of central tendency are. But again, back at the original definition that we talked about, central tendency, we want to know, what does the center of the distribution look like? And so one of the very simple distributions that we're going to introduce for the rest of this class today, and then as we go into the lab tomorrow, is this very simple distribution of 15 values. all ranging from 0 to 10. It's as simple of a distribution as you're going to get. But it's a really good one because you can actually just take out your calculator and take out your phone and play around with this. And really, it will come to life what these different measures and how these different measures are used. So we're going to use this. We're going to come back to this as we measure every different piece of central tendency and also dispersion and variance. So the mean as a measure, this is probably the most natural because it's the average. We're used to thinking about averages. Human beings are very, we're kind of wired to think about averages. We talk about averages in our daily life all the time. And that's really all a mean is. And you look at these calculations and you're like, that's way too complicated. Why? It's just the average. But that's exactly what these are showing. And we're not going to break it down, the sigmas and the mu's and all that stuff. The only thing I'll say about it is that one thing you'll notice, we introduced this a while back, I promised we would revisit it. You'll notice that there's a population data and there's sample data. These are basically the same formula. The only difference is that in the population data, you see there's a lot of Greek letters. Sigma, which is the sum of, that just means you're summing the values. X1 just means each individual value. So you're summing all these individual values in your data set. So that's like adding all these numbers up. That's all this means. Sigma X. And then mu is the Greek letter for the average of the population. So populations, Greek letters. Samples, English letters. So you look at the associated instead of mu for the population. When we have a sample, we have X bar or the mean. So that's represented by this X with a bar on top. And then again, you have the summation, but now we're working with a lowercase n. That's the sample size. Same thing. All this is saying is to get the average, we're summing all of the values and we're dividing by the number of values. What's the average? Now, one of the things we talked about with skewed distributions is that every now and then when you look at a distribution of data, you're going to get some extreme values. And the mean is very sensitive to extreme values. And this is one of the shortcomings of the mean. As we talk about what measure of central tendency is best, what best describes the center of a distribution, this is really, really important for you to understand that when we're looking at the mean or the average, it's very sensitive to outliers in your distribution. Take that compensation data, for example, and I'll show you an example in this data set in a bit. But if you took income or wealth in the US and you included Elon Musk and Jeff Bezos and Mackenzie Schneider, I think is her last name, and all these super wealthy, Taylor Swift, and all these super wealthy people, what's going to happen is the average is going to be dragged out toward the outliers. The mean is very, very sensitive to extreme values in a distribution. Very important to understand. And we'll talk about that multiple times. So let's talk about calculating the mean. So if you were to take the time here on your phone really quickly or on your calculator on your computer, and you took all these values, that's the same distribution we just looked at, right? Bunch of simple values, 15 numbers, n equals 15, and you added all those up, you would get 75. To calculate the average, very simple. 75 divided by 15 equals 5. So in this case, the average or the mean of this distribution is 5. Very straightforward, very simple. That's essentially it. That's how you calculate the mean. Now, there are a couple of considerations and very important points. One, the mean is the most commonly used measure when we do inferential statistics. So at the very beginning of class, I mentioned what we're going to cover today is going to be essential for your understanding of what we're going to cover next week, which is going to get progressively more complex. The mean and your understanding of what the mean is crucial because we're going to use the mean over and over and over and over, not only in inferential statistics, but also to calculate measures of variance, like standard deviations and variance itself. Let's see. Yep, we talked about this. The mean's very sensitive to extreme values. If you have a skewed distribution, the mean is going to drag toward the tail. You're going to tend to see that mean get pulled toward the tail of a skewed distribution. And in those cases, when it's very skewed, sometimes the mean isn't the best measure of the center of the distribution. Okay, let's talk about the median. The median may not be as familiar, but it's also fairly simple to understand. And so what we do in the median, as we talked about, the mean is the average, the median is the exact center of your distribution if you rank ordered the values from lowest to highest. So that's exactly what we do here. So if you want to calculate the median by hand, you might take that distribution. We'll do this on the next slide. And you just order it in ascending value. What's the lowest value in your distribution? What's the next? What's the next? What's the next? What's the next? And you keep doing that till you finish to the highest. And then you find the center point, the centermost value, and that becomes the median. And this is particularly useful when we are looking at skewed distributions, because the median is not nearly as impacted by extreme values or outliers as the mean is. And so we'll talk about that in a minute. And you can see that in this last bullet point. So let's look at that distribution of data again. Same distribution of data, right? We have those very simple numbers. And we found last time the mean was 5. And in this case, what we did was we just took that data set and we reordered it and we put it from lowest to highest. So we have a bunch of 2s, got a bunch of 3s, we got a 4, we got some 5, 6, 7, 8, 9. And then we count and we find that the exact middle value is 5. So for this simple distribution, your mean's 5 and your median's 5. Now, this is an odd number of values. This is 15 numbers in your distribution. Let's say you had 16. I'm gonna just do that for the sake of argument. Let's say we added a 9 there. Well, now this isn't exactly the center of your distribution anymore. The center of the distribution is actually both of these numbers. Because remember, it's right. So what do? Well, you just take both those numbers and divide it by 2. And that 5 plus 5, 10 divided by 2 is 5. So if that happened, your median would still be 5. And so that's the only little minor tweak in calculating the median. If it's an odd number of data in your distribution, and you're doing it by hand, it's going to be that middle number. If it's an even number of values and there's 2 numbers in the middle, you just find the average of those numbers and that becomes your median. Any questions really quickly about median and mode? Mean and median. Pretty simple, right? Pretty straightforward. Not that hopefully this is kind of demystifying some of this stuff. So let's talk about a couple of considerations. This is a really good illustration of what happens in a skewed distribution or extreme values. We talked about the mean. The mean, what happens is it tends to get dragged toward the tail of a distribution, of a skewed distribution. The median is not nearly as affected. So let's say, for example, we had that very simple data set where the mean was 5 and the median was 5, right? But let's say we made a mistake and we forgot one data point. And let's say we're messing around. I was messing around with the data and Chris came to me. He's like, Ben, you missed a data point 25, right? So we have this super extreme value because all the rest of the data is like 2 to 4 to 5 to 9. And then there was this one value that's way off the charts high. But it's part of this distribution of data and we just forgot to add it. So we added this number back in. Well, if that were the case, if we recalculated the mean, look at what happens to the value of the mean. It goes up a substantial amount. It was 5 before, but when you add that one value, big value, it jumps up all the way to 6.25. That's a pretty sizable jump in the mean. But notice what happens to the median. Didn't change at all. All we did was add one value to the end, so the median just moves over 1, which is still 5, because now we're just averaging these two values. But the mean really gets pulled out pretty substantially, a whole 1.25 points over with just one extreme value. So that's a very simple illustration of what happens in a skewed distribution where you have those extreme high values or extreme low values that drag the mean out with it, but it doesn't really affect the median all that much.
Extreme high values on one side of the distribution. It's an important, which is implied when we say skew, but I just want to say it out loud again.
Yeah, good point. Good point. Okay, almost done with central tendency. The mode, this is really simple. The mode is the most frequently occurring value in the data set. What number or value shows up the most? So the mean is the average, the median is the middle, the mode is the most frequent. And so essentially you can use the mode in both numerical or categorical data. The mode is especially useful when you have categorical data where you can't really calculate a mean or a median. That's nonsensical because there's no like value. There's no values to average or to compare, or the order of those values is not meaningful. They're just categorical. I'll show you an example here in a minute of ice cream flavors, right? So if we did a study of, I think somebody was eating ice cream earlier in the class, what's your favorite ice cream? And we went out to a bunch of people and we asked, okay, well, who likes peach? Who likes strawberry? Who likes vanilla? Who likes chocolate? Well, we can't really calculate a mean or a median for that, right? But you can calculate a mode. And the mode here would be chocolate. So mode is a really effective measure of central tendency when you have categorical data or non-numerical data or non-continuous data, in other words. Really good measure. But you can also use it in when you have numerical values or continuous data. And so in this example, for example, same data set, right? We looked at, we know that the mean's 5, we know that the median's 5, but the mode is actually different. The mode is 3. It's the most frequently occurring value in the distribution. So to kind of summarize that, we got the mean, that's the average, the median's the middle. If you rank order things from low to high, the mode is the most frequently occurring value. And to show and illustrate what I was talking about earlier, when we map those values to distributions, what you tend to find is in a perfectly normal symmetrical distribution, those values will be very close to the same. In a perfectly normal distribution, they're exactly the same. But in a generally normal distribution, which is more commonly what we would find in research, they'd be very close to each other. But if you're calculating central tendency and you notice that the mean and the mode and the median are wildly different from each other, that's a pretty good indication that you got a skewed distribution. And you're going to see that some live data tomorrow that shows that. And look at how they differ. In a negatively skewed distribution, what happens is the mode ends up being the top of the peak. Because remember, the x-axis is the values, the y-axis is the frequency. And what's the mode? The most frequent value. And so the mode is going to be where that curve peaks, the peak of the curve. The median might get pulled a little bit to the left, but look at how far the mean gets pulled, right? The mean is really sensitive to those extreme values. Same thing on the positive side. If you have a positively skewed distribution, the mode's the top of the peak of the curve, the median's a little bit further to the positive side, and then the mean really gets dragged out by those outliers in the distribution. So this is also a really good kind of cheat sheet visual of when you're looking at, when you see the mean really high, it's a lot higher than the median, and the median's a little higher than the mode. It's a pretty good indication you got a positively skewed distribution. If the opposite's true and your mode's a little bit the lowest, and I'm sorry, your mode is the highest value and your median's a little bit lower than that, and your mean's a lot lower than that, you got a negatively skewed distribution. And this also helps you to determine when you are deciding what's the center of the distribution, which measure is the best to go with. The type of the data you're using, whether it's categorical or numerical, and also what type of skew you have in your distribution of data is going to give you a good hint as to what you should use. Okay, so we did not get to dispersion yet. We're going to have to push that to tomorrow. We had a little bit of an exercise, but let's save that for tomorrow. And so let's jump really quickly. We'll pause here for today. Yeah, let's answer a couple questions actually and talk about tomorrow. So Chelsea, explain, not sure I'm following your question. Could you explain that a little bit?
Yeah, so like when, I don't know, when you're, maybe this is more for variance and the other one, dispersion?
The
No, what
standard
was
deviation and
standard
variance?
deviation?
Mhm.
Or is that usually measured against the mean?
Yes, we're going to be using the mean to calculate those. So I'm gonna jump back to these for you, Tyler. We want to
And
take
then
some screenshots. But yes, the
how do
mean,
you,
even in those skew distributions, we're going to be using the mean to calculate the variance and the standard deviation. And we'll jump into those calculations tomorrow.
okay. When you're looking at this on a graph and you're talking about, um, the mean and the mode and the deviations and the skewness, how do you translate that to a universal language when you're talking to like a CEO? So you're taking this information, you're digesting it, but then what are you saying to whoever you're needing to communicate this kind of data to?
Yeah, that's a tough question to answer quickly. What I might
Okay.
say, I'll give you a brief answer and then where I will actually come back to that at the end. That is a very good question.
I have
Um,
a couple of thoughts if you don't mind.
yeah, go ahead, Chris.
Uh,
Yeah.
So I like to translate fancy speak into typical common language, right? So I might lead and say, the median of the data was 75. But rather than say medium, I might say middle, the middle of the data, right? Or the middle meaning about half or above or half below. One that I invented myself that's for standard deviation. I call standard deviation the plus or minus metric, right? Meaning if the average is, take IQ. IQ is an average of 100 with a standard deviation of 15, right? That's just for IQ. So standard deviation is 15. So I would say IQ is 100 plus or minus 15, the plus or minus metric. Plus or minus 15, if you go back to that bell curve, that means 2/3 of people, almost 70% actually, are plus or minus. They're between 85 and 115, right? So you can take fancy terms like standard deviation, understand what they actually mean, plus or minus in a standard deviation, and then translate it into something that's going to resonate with a business partner. And if they want to go deeper, you can go deeper with them. But finding ways to kind of translate stuff into common language is a really powerful way to bring folks along with you, because if you start using Greek letters and saying fancy words like kurtosis, you're going to lose them, right? And it's one of the reasons to understand this stuff deeply, because once you understand it deeply, you'll be able to use your own natural language to explain it to people. If you only understand it a little bit, you kind of got to fall back to the textbook language, and that's where it starts to get tough.
That I love that you pointed that out. That very much goes to a point that I made before about scientific humility. And one of the heuristics I use is when I run into somebody, and you could probably charge me and Chris for doing this in this course, but you can excuse us because of the academic course, and we're trying to teach you about this stuff. But if you run into somebody who's using all these fancy terms and they're throwing all, when I run into that, I immediately assume, whether it's right or wrong, my assumption, my heuristic is that person does not understand this well enough, because they can't simplify it. There's a great Einstein quote. I can't remember exactly the phrase he uses, but it was something like, if you
don't
can't explain
understand
it to a
well enough
5-year-old.
to explain it simply.
Yeah, exactly. If
You
you
don't
basically,
understand it well enough to explain it simply, you don't understand it well enough.
exactly. So that's a great point Chris brought up, is that we are going to introduce this stuff to you so that you can understand it deeply. But Chelsea, that's a fantastic question. And really what we're going to do in the last 2 weeks is how to take all this fancy stuff and communicate it effectively so that somebody who doesn't know all this stuff about statistics that understands what it means and then goes and does something with it. Because if they don't understand it, they're not going to do anything with it. And then you've wasted your time. There you go.
Yeah,
Thank you,
and
Chris.
you kind of become a little bit of a kung fu master as you get good at this, because you also learn to sort of avoid the lexical landmines of your stakeholders, because they'll say, what's the average? And you know they mean typical. But if you then go off on a tangent to explain to them the difference between median and mean, you're going to
Yes.
lose them. So
Yes.
don't do that.
Yes.
Say, you clarify, say, oh, are you trying to understand what the most typical responses are? Yes. Cool. And then you just start talking about the median. You don't have to bring them on that journey where you're trying to school them, right? So a big part of executive communication is learning to understand what people mean, despite what they say, and then explaining things to them in a way that's accessible for them.
Yep. Excellent points. Okay, so I know we're at time. We'll pick back up here tomorrow with a little exercise. We'll go through this and then we'll try to spend the rest of the time focusing on the working with your data set. So tonight there's a couple of very short videos. I think there's maybe just one short video, but the most important
One
piece,
video and a long video.
yeah, there's one short video. It should take you like 10 minutes. This video, absolute necessity that you watch this before tomorrow. And because we're putting that much pressure on you, absolute necessity that we grade some of the vignettes tomorrow. So holding ourselves accountable to that. And we'll give you a little bit of feedback. We have a ton to cover tomorrow. So I'm going to figure out what's the best way to give y'all some feedback. What I might try to do, since we have a lot to cover tomorrow, is I might try to provide you some feedback on the vignettes through Canvas, either verbally or in text. And maybe we can spend a few minutes, but we'll try to get you some feedback on those before tomorrow. But absolutely critical that you watch Chris's video. You have Excel ready to go. And another thing that Chris is going to talk about in the video is how to add on the stats package within your Excel version. It's pretty simple. He does it for I think a PC. If you have a Mac, it's very straightforward. Just Google it. But if you do have any problems, do this early, like do this tonight or tomorrow morning. And if you have trouble, just email us. Thank you, Brittany.
Yeah, I walked through it. I walked through it for PC users, but I just dropped the Mac
Oh,
tutorial.
okay, that was you,
Everybody's
Chris.
using a Mac.
Cool. Okay. Well, I know we're a little bit past time. We're going to cover dispersion tomorrow. That's a little bit more complicated. It's going to build on what we talked about tonight. We're going to talk about a concept called Z-scores, which is a really useful tool that's going to be helpful for you. And then we're going to dive in and we're actually going to do some work in Excel on your final project data set to kind of give you a head start and make sure that you're not, we're not just throwing all this stuff at you and saying good luck. So we're going to try to work through it together to give you an opportunity to work with us there and with your peers there. Any final questions? Any final thoughts before we close out tonight? All right, cool. Well, thanks so much for your attention. Thanks for the engagement. Thanks for the feedback, and hope you all have a good night. We'll see you tomorrow.
Great. Thanks, guys.
Hi, thank you.
Thank you. Have a good night.
Ben, if you'd like, I can